Alright, so here's our extra credit lesson 3.13. It's just an extension of using L'Hopital. As you guys know, with L'Hopital, we use L'Hopital whenever it's 0 over 0 or infinity over infinity. But there are other indeterminate forms like these three here that are not L'Hopital ready. You can't do anything with these expressions when you have those indeterminate forms. But what we're going to do is we're going to do some algebra tricks today to deal with those. So let's go ahead and take a look. There's basically those three types. So for these ones, the strategy we're going to use, the algebraic strategy, is we're going to use reciprocals. Okay, you'll see what I mean when we get there. The strategy we're going to use for this one is we're going to basically combine the two expressions together that give us these infinities. We're going to have two of them. We're going to combine them together into one. And then for all these ones that involve some kind of an exponent or something like that, we're going to use the natural log somehow. So those are the three different types of indeterminate forms that we haven't talked about yet. And these are the algebraic strategies we're going to use to transform them into either infinity over infinity or 0 over 0 so that we can actually do L'Hopital in them. So basically that's it. What makes this so difficult is just basically the algebra involved. It takes a lot of algebraic manipulation to get these things to be what you want. This one is the easiest. This one is not too bad. But honestly, the last two are the last one for sure is usually pretty ugly. The middle one can be. It just kind of depends. Just a whole lot of algebra going on there. So we're going to start off with the easy one first, and then we'll jump into the other two. Here we go. All right, so that's one of the uglier ones. Let me see if I can find a better one. We're going to go ahead and start off with this one. This is one of the easier ones. Okay, so by direct substitution, we get 4 times infinity, which is infinity. And then here, we plug in infinity, this whole thing becomes 0. And sine of 0 is 0. And that's an indeterminate form. And the strategy I told you guys we were going to use for that was we were going to do reciprocals. Okay. Now what I'm gonna do is I'm gonna make use of an awkward algebraic fact. For instance, before we start solving this problem, let's review something. If I had 1 over 2, what would that simplify to? Well, if we multiply the top and the bottom by 2, we get 2 over 1, so it's really just 2. So here's the point. 1 over 2 is 2. We're actually going to work backwards, though. We're going to have something like this, and we're going to turn it into something like this. Okay? So we're going to do reciprocals, so to speak. So here we go. We're going to do it to this guy right here. Okay? So I'm going to rewrite this expression. And instead of having 4x on the top, what I'm going to do is I'm going to put on the bottom 1 over 4x. It's exactly, using the properties of fractions and reciprocals, it's actually exactly the same thing. But by doing that, remember how this was infinity times 0 before? I think I got them backwards. It was infinity times 0. It doesn't really matter. But now let's see what we get. If I plug in 0 here, I get... I'm sorry, not 0. If I plug in infinity, I get 0, and sine of 0 is 0. If I plug in infinity here, I get 1 over infinity, which is also 0. And now we've got L'Hopital. So as you guys can see, that little trick that I just employed there allows me to apply L'Hopital's rule. Okay? So now we get to do some more fun stuff. Let's go ahead and take the derivative of these. So let's take the derivative of this one first. Okay. I'm going to show you one time how to do this, and then after that I'm going to let you guys worry about figuring it out after that, because it's just review. How do you find the derivative of 1 over 4x? Well, the first thing that you do is you're going to write it as x to the negative 1, right? You take the x, put it on the top, give it a negative exponent. And then when we take the derivative, you multiply it to the front. So let's actually take the derivative here. So we multiply 1 to the front, and we get negative 1/4. And then you take 1 away from the power, and you get negative 2. And then final answer, we'll go ahead and we'll just put the x squared back in the bottom and change the power to a positive again. So that's how you do the derivative of 1 over something with an x on the bottom there, right? And so in this case, we have the limit as x approaches infinity of 1 over 4x squared, and it's negative, right? And then we're also going to do the same thing on the top, okay? So on the top, we're going to take the derivative of sine, which is cosine, and we won't change the inside. We're going to leave that alone. But we will take the derivative of the inside, and you're going to take the derivative of that in the same way that you just did the 1 over 4x. You're going to give it a negative 1 exponent, and you're going to multiply it to the top, etc. I guess I'll do it one more time just to kind of keep you guys fresh with it, but after that I'll kind of assume you guys will know how to do it. So 1 over x can be rewritten as x to the negative 1. The derivative, I'll just put d here for derivative, would be negative 1 x to the negative 2, which can be rewritten as negative 1 over x squared. So the derivative of the inside is negative 1 over x squared. Okay? So now before we do any direct substitution, what we're going to do is we're going to simplify this now. We went ahead and we changed the form so it fit the L'Hopital rule, and that now allows us to take the derivatives, but now we're going to simplify it back. So now what I want to do is I want to rewrite the reciprocal a little bit differently. So instead of having negative 1 over 4x squared in the bottom, I'm going to multiply the top and the bottom by 4x squared. What the heck, we'll make it negative 4x squared, so those cancel and the negatives cancel. And we'll multiply the top by negative 4x squared as well. And so the negatives cancel and the x squareds cancel. And so we're left with this then. And now we do our direct substitution again. So plugging in infinity, we get 0 here. Cosine of 0 is 1, and therefore the answer is 4. Okay, there you have it. So a lot of crazy algebra there, but basically we get, when you have infinity times 0, the one that's an infinity, what we can do is we can write it as a reciprocal in the denominator, which therefore changes it into L'Hopital, which allows us to take the derivatives, which you got to remember how to do your derivatives. And once you simplify that expression, your outcome, you should be able to do direct substitution and get your answer at that point. Okay? So that's the first case, when you have 0 times infinity. Let's go ahead and take a look at one of our other cases. So in our beginning of our lecture day, we said we're going to talk about 3. That was the first one. Now let's take a look at another one. Let's try one with the subtraction on it. See if I can find one there. This will work. Okay. So in this case, if we were to do our work, we'd plug in here, and what we would get is infinity over infinity and then minus over here we would get infinity over infinity. Now both of those are indeterminate forms, which means we can apply L'Hopital's rule to each one separately, right? By the way, you can also use the strategy that we learned in lesson 3.9 for those. But I'll go ahead and stick with L'Hopital for now. So the derivative of the top is 2x, the derivative of the bottom is 1. And so if I plug in infinity, I get infinity. The same thing is going to happen over here. Derivative of the top is 2x, bottom is 1, and that's infinity. And we're subtracting them, and there's your other indeterminate form, right? So we can't do L'Hopital on this, but there's a way we can mess with it so that L'Hopital will work. Or maybe once we mess with it, we won't even need L'Hopital. We'll see. The strategy when you have infinity minus infinity is to combine the two expressions. So these two expressions here, I'm going to combine them. What I'm going to do is I'm going to multiply this one over here by x plus 1 on the top and bottom. And I'm going to multiply this one over here by x minus 1. That way, both of them will have the same denominator. They'll both have an x plus 1 and an x minus 1. Let's see what we have after we do that cross multiplication there. Here, if I distribute, I'm going to get x cubed plus x squared. And on the bottom, I'm going to have, I guess we'll go ahead and just multiply it out. It's pretty easy. That's going to be x squared minus 1. Minus over here, distribute. So now we've got these two expressions with a common denominator, and we combine them. This negative needs to get distributed across here. So we end up with the limit as x approaches infinity of x cubed minus x cubed is 0. So those cancel. And then x squared minus a negative x squared, that's like plus, right? When you subtract a negative. So I've got x squared plus x squared, which is 2x squared over x squared minus 1. And honestly, at this point, you could just write your answer if you remember your strategy from lesson 3.9. In lesson 3.9, we realized that when these powers are the same, the limit will just be this number over this number. That's the easiest way to do it. You could also do L'Hopital with this, though. If you plug in infinity, you get infinity over infinity, so you just take the derivative and keep working on it until you get an answer. But either way, you're going to get 2 as an answer. Okay, so that one was deceptively easy. So watch out. I mean, they're not always quite that simple. But the main strategy is that whenever you get infinity minus infinity, the concept is combine them. And then go ahead and apply L'Hopital after that if you need to. Or if you see another strategy you can apply, you can do that too. All right. We'll do one more. Now this last set is going to be a little crazy here. So in this case, if we do our direct substitution, sine of 0 is 0 and tangent of 0 is 0. This is an indeterminate form as well. Now when you have this situation, the way that you handle it is with an ln. So once again, going back to the beginning, our first problem we did this. Second problem we had this. Third problem we're looking at these kinds, where you have infinities and zeros with powers of infinity or 0 on them. So that's the last one. The strategy for that is ln. So I'll show you guys how these ones work. They're pretty crazy. But hey, this is AP Calculus. We kind of expect a little crazy sometimes. So let's see, it's tangent x sine x. So here's what we do here. The first thing is I'm going to say, I don't know what it equals. So let's just say it equals y. And that means my goal now is I want to find out what y is. Now the reason I did that is because my next step is going to be to take the natural log on both sides. It's a weird thing to do, but I'll explain why in a little bit. For now, just let's do it. All right, first of all, that makes this kind of like a composite function, right? And we've learned about limits with composite functions. They can be written outside or inside. So the next thing I want to do is I want to take the limit out of this log and just write it in the front again. So it's going to look like this. So now I've got the log right next to this tangent expression here. Okay. Now the reason we did log is this. We don't like this power being here. And when you have a log, there's a rule about that. The rule is you're allowed to take the power and slide it to the front. That's a logarithmic property. So I'm going to put the sine x in the front now, and then I'll put ln of tangent x. This side's going to stay the same until we get to the very end, but for now that right side's just going to stay exactly the way it is. So now I've got sine being multiplied with ln of tangent. Now if I was to do direct substitution, sine of 0 is 0, and tangent of 0 is 0. And ln of 0, if you remember from yesterday's lesson, is, or not yesterday, 3.12, whenever you watched that, is negative infinity. And that's an indeterminate form. That's another indeterminate form. So we started off with the 0 to the 0, but this whole ln thing allowed us to change into this. And that, in case you guys don't remember, we have an issue with, right? We already know how to do that. The strategy for that one is to do reciprocals. So that's how the ones that have 0 to 0 always work. They will, first strategy is the ln thing, and by doing that, it changes it from this kind of an indeterminate form into this kind of an indeterminate form. And so that way we can do our whole little reciprocal strategy that we learned earlier. So here's what we're going to do. We're going to take this and we're going to put it in the denominator as a reciprocal. So let's do that. So now I've got the limit as x approaches 0 from the right. And on the top, I believe it wasn't it ln? Ln of tangent x over 1 over sine x. And all the while, ln of y is just sitting there. Okay. Now what? So we go ahead and try our direct substitution, right? And what we get with our direct substitution, I'll show my work here. You don't necessarily need to. But if I plug in 0, tangent of 0 is 0. Sine of 0 is 0. And we know from lesson 3.12 that this is negative infinity. And we know from lesson 3.11 that this one is either going to be positive infinity or negative infinity, depending on what direction we're approaching from. But it really doesn't matter in this case. Now, if this were just a regular polynomial, we would probably say positive infinity, but this is sine, and sine might behave a little bit differently. So all we know is it's either going to be positive infinity or negative infinity at this point. So, but here's the good news. Regardless, we have an infinity over an infinity, and that's L'Hopital time. So we've done it. We haven't solved the problem, but we've gotten to the point where we can use L'Hopital. So let's review really quick before we go any further, because that's the main thing. We had the indeterminate form 0 to 0 power with our direct substitution. The strategy for that is to ln both sides. The purpose of the ln is so we could bring the power to the front. And by doing that, instead of having 0 to the 0 power, we end up with 0 times infinity, which is a different indeterminate form, which we already have a strategy for, and that is by doing reciprocals, taking the sign and putting the reciprocal on the bottom. Then direct substitution gives us a L'Hopital ready form. So that means this form now is ready for L'Hopital. Okay? Now, The trig functions add an extra layer of difficulty, as they typically do. We could leave it as 1 over sine x. I don't know if yeah, I guess we'll try it. It might be easier to change this just to cosecant, okay? It's kind of hard to say what we should do. It just depends on how comfortable you are with all of your trig identities and stuff like that. I think what I'm going to do is I'm going to go ahead and rewrite it like this. I'm just going to make sure everything is in sine and cosine. I think things work a lot easier when you do that. So let's leave it like that for now. I am going to change this to sine x to the negative 1 power though. So there's that. Now let's go ahead and take our derivatives. Since we have infinity over infinity, we can do L'Hopital. Let's take our derivatives. So the derivative of this on the top is going to be 1 over tangent. And then we're going to multiply this by the derivative of tangent, which is secant squared x. Now we have on the bottom here, we've got sine x to the negative 1. So I'm going to do, this is a chain rule. We're going to multiply the front by a negative. Don't change the inside. Take 1 off the power. Then we're going to multiply by the derivative of the inside, which is cosine x. Ew, lots of nasty stuff here. All right. So at this point, this is very messy. So I'm going to start cleaning it up and using some trig identities to simplify it. And once it's all simplified, we'll try direct substitution again and see if either A, we have to do L'Hopital again, or B, maybe we'll finally get an answer. So the first thing I'm going to do is I'm going to rewrite this as 1 over, I'm going to change the tangent to be cosine x over, no, it's sine x over cosine x. I'm going to change the secant squared to be 1 over cosine squared x. I like everything to be in terms of sine and cosine. It just makes it easier to simplify, in my opinion. And then we have negative here on the bottom, right? Cosine is going to end up being on the top because of this guy, and then we have sine squared on the bottom. So we have basically a complex fraction here that we need to simplify.
I just saw Noah. Where is he? Oh, sorry.
The first thing we're going to do is we're going
What is your
to
quote supposed to mean?
cancel this with one of these cosines over here, because this is like cosine over 1. So the cosine on the bottom here cancels one of the cosines here. So let's do the following. We would have 1 over sine, and it looks like it would end up being cosine also on the top. But on the bottom, we still have this.
Daniela said Miss Chu's doors last summer.
All right.
All of us.
Hello. The next thing you're going to do is you're going to multiply the top and the bottom by, let's do this one to simplify our complex fraction. So I'm going to do sine squared x, sine squared x. So in this case, these cancel, right? And this sign will take one of these signs away. So we're getting there. So we have now. All right, so on the top we have, write this again, sine x over cosine x. And on the bottom, we're still left with a negative cosine x. We're getting there. Let's keep going. The next thing I want to do is I don't like this fraction on the top, so now I'm going to multiply the top and the bottom by cosine x. Cancel that out. And we're left with this now. So we have negative sine x over cosine x squared. And now I think we're ready for our direct substitution. So that we had to do a whole bunch of simplifying there with trig properties, but direct sub and direct sub. The top is 0, the bottom is 1, and so the final answer would be 0. Now before you get too cozy and conclude that the answer is 0, I want you guys to remember that this whole time this limit equaled ln y, right? Let's back up a little bit. Remember how this whole thing equaled ln of y? So what I just proved is that that limit equals 0, and it equals ln of y. So what that means is that our limit equals 0 and ln of y. So now we're going to solve for y. How do you get rid of the ln? You exponentiate both sides, and those cancel. So you have e to the 0 equals y, and that means y equals 1, and that is your final answer. And I'll go ahead and post up your guys' exercises here. Alright guys, so here are your extra credit exercises. One of each. Okay? So good luck, and we'll see you guys later.